So in this installment of Chapter 9, we'll go over questions dealing with chemical reaction rates and chemical equilibrium. And so we'll start off with question 5 from Chapter 9, which asks, what happens to the number of collisions between the reactants when the temperature of the reaction is increased? So in this case, we want to remember that when we increase temperature, that means we're going to increase the speed of the reactants, increase the speed of the molecules. And when we increase the speed, we also increase the collisions. So we're going to increase, when we increase temperature, we increase the speed because we increase the kinetic energy. And when we increase the speed, we're going to have more collisions. And so in number 5, it would be increase the number of collisions. In number 7, it asks, if a catalytic converter accelerates the reaction of carbon monoxide with oxygen to produce carbon dioxide, then what's going to happen to the rate of the reaction from all of these following changes? And so in A, what's going to happen to the rate of reaction when we add more carbon monoxide? So here we're going to add more carbon monoxide. We're adding more of the reactant. And so when we do that, then we're going to have more collisions of the carbon monoxide and the oxygen. We have a greater chance of the carbon monoxide and oxygen colliding with one another because we have more carbon monoxide. And so if we have more collisions, we're going to have a faster rate. So we're going to increase the rate. And then in B, it asks what happens if we raise the temperature. So this is very similar to the question above in number 5. If we raise the temperature, then we're going to increase the kinetic energy. So if we increase the temperature, then we are going to increase the kinetic energy. Then we're going to increase the speed. And so if we increase the speed, we're going to increase the collisions, which is a faster rate. So we're going to increase the rate of reaction in B. C, removing the catalyst. So the catalyst, if you remember, is a catalyst decreases the activation energy. So it allows the reaction to occur by not needing as much energy to make the product. It finds that shortcut. And so if we remove that catalyst, then the reaction is going to need more energy. And so if the reaction needs more energy, it's going to slow it down. So if we remove the catalyst, then we're going to increase the activation energy. And if we increase the activation energy, we decrease the rate. And then in D, it asks what happens if we remove some oxygen, some O2. So here we're removing the O2. So if we remove O2, we are going to decrease the possibility or the probability of the carbon monoxide molecules colliding with the oxygen molecules. So we're going to have a decrease in collisions. So if we decrease the number of collisions, then we're going to decrease the rate. So in A was increase. In B, it was increase. C, decrease. D, decrease. Now we'll look at number 13. Ask us which of the following are at equilibrium. And so A says the rate of the forward reaction is twice as fast as the rate of the reverse reaction. And so, if you remember from the PowerPoints, one of the main points that was made was that when we reach equilibrium, that means the rate of the forward reaction is equal to the rate of the reverse reaction. And so here, in this case, it's saying that we have the forward reaction is twice as fast as the reverse. So here, we are not at equilibrium. In B, it says the concentrations of the reactants and the products do not change. So if you remember from that chart, all right, we had the number of reactants was going to decrease as time went on and then flatlined. And then the number of products increased and then flatlined. And then this point is where they do not change anymore. Now they don't have to necessarily be equal. In this case, I just drew it to be that. But the important part is that they are not changing. And so, yes, these are at equilibrium. And then C, the rate of the reverse reaction does not change. Well, if we draw another chart of the rate of reaction, so this is rate and this is time, the rate of the forward reaction is going to decrease over time and then flatline. The rate of the reverse reaction is going to increase and then flatline. And then these points, must be equal. And so the rate of the reverse reaction will not change when it's at equilibrium. So that is true. So yes, this would be true. And that would be at equilibrium. Now we'll look at number 17 from chapter 9. And it says, identify each of the following as a homogeneous or heterogeneous equilibrium. And so all this means is that if it's homogeneous, it's going to have all of the same physical states. If it's heterogeneous, then it's going to be having different equilibrium states. So in A, we have both the reactant and the product both in the gas phase. And so since they are both in the gas phase, then they are going to be homogeneous. So we'll write it as homogeneous. Then in B, we have the one reactant to be a solid, and we have three products. And the three products, we have one solid and we have two gases. And so since we have a mixture of physical states, that would imply that we have a heterogeneous. In C, we have two reactants and two products. The two reactants are gases, the two products are gases. And so we have all the same physical states, so we have a homogeneous equilibrium. And then in the last one, we have two reactants. We have a gas and a solid and two products, two gases. And so in this case, we have a mixture of physical states, heterogeneous. In 19, it asked us to write out the equilibrium constant expression for these following reactions. So what we have to remember is that Kc is equal to the concentration of products over the reactants. All right. And another thing we have to remember is that when we use these concentrations and when we use these balanced equations, we'll have to use the coefficients in the balanced equation as our exponents in the chemical equilibrium constant expression. So in A, it's products over reactants. So Kc is equal to the concentration of O2, which is our only product, over our only reactant, which is ozone, O3. And so now we just need to go back and use the coefficient. So oxygen, O2, had a coefficient of 3. So that 3 becomes our exponent. Our ozone, 2, our ozone had a coefficient of 2, so that 2 becomes the exponent. Do another one. In B, we'll have to use not only what we did in A, but when we have these heterogeneous equilibriums, and we have solids and liquid states, those solid and liquid states we don't use their concentrations, and so we basically put those values as 1. And so if you have a chemical equation in which you use any molecules that are in the solid or liquid state, you use their concentrations as 1. And so they basically become negligible. You just ignore them pretty much. So here, Kc is still going to be products over reactants. So we have 3 products. The first one, sodium carbonate, is a solid, so we don't have to use that one. So then we skip to the carbon dioxide. So we have CO2. And then we have the other product, water, H2O. And then our only reactant is sodium bicarbonate, NaHCO3. And so in this case, then since it's a solid, we don't have to use it in the equilibrium constant expression. And so then we can go back and we can look at our balanced equation and see if there's any coefficients. And so we only have to look at CO2 and H2O, and they both have coefficients of 1, and so our exponents are 1, so we don't really need to add it in. And so then we'll look at C. Kc is going to be products over reactants still, so our 2 products, H2 and CO. Then that's going to be over reactants. We have methane, and we have water, H2O. We can go back and we can fit in our exponents. So hydrogen had a coefficient of 3, so it has an exponent of 3. Carbon monoxide, CO, has a coefficient of 1, so an exponent of 1. Methane, coefficient of 1, exponent of 1. Water, coefficient of 1, exponent of 1. So we're all done. Then lastly, in D, here we have another heterogeneous. So again, we can pretty much ignore these solid states. And so we have Kc equal to products over reactants. So we have silicon tetrachloride and hydrogen gas as our products. And then we have HCl, hydrochloric acid, and then silicon as our reactant. So we don't need to use the silicon because it's a solid. Silicon tetrachloride has a coefficient of 1, exponent of 1. Hydrogen has a coefficient of 2, so an exponent of 2. HCl has a coefficient of 4, so it must have a exponent of 4. And so that would be the equilibrium constant expression for those examples. Now moving on to number 21. It asks us to now calculate the Kc, or equilibrium constant, for this following reaction. So what is nice is that it's already balanced for us, so we don't need to do that step. And so now what we can do, we recognize that we have this concentration, and we see now we can go and write out our equilibrium constant expression, which Kc is equal to products over reactants. So we have NO2 over N2O4. And so here we see a coefficient of 2, so that must become the exponent of for NO2. Coefficient of 1, exponent of 1. That's all well and good, and now we need to calculate the Kc. So we plug in our numbers. Our NO2 concentration is 0.21, and that is squared. And our N2O4 is 0.030. So we can calculate this out. We get 0.21 squared divided by 0.03, and we get a value of 1.47. Now we'll move on to number 23. In this one, it wants us to calculate the Kc for this following question and reaction. And so, just remember that it says it's at 1,000 degrees. And so remember that equilibrium constants are specific to temperature. So when you change temperature, you change the equilibrium constants. So this one is specific for 1,000 degrees Celsius. And so we have all 4 concentrations. So we just need to write out our equilibrium constant expression. So it's products over reactants. So we have methane, CH4, is a gas. Water is a gas. Carbon monoxide is a gas. And we have hydrogen as a gas. And so now we just have to go back and look at our coefficients. And so the only coefficient we need to be concerned with is hydrogen, which is 3. So once we have that, then we can go and put in our numbers into the expression. So methane had a concentration of 1.8. Water was 2.0. We have carbon monoxide as 0.50 and hydrogen as 0.30, and that 0.30 must be cubed. So now we just plug it into our calculator. And we get a value of 2.7 times 10 to the 2. And the reason why I did that was just to keep the number of significant figures consistent. So since we are doing all multiplication and division, we use the least number of significant figures, and therefore we should only use 2 significant figures. I think in the last problem I used 1 too many significant figures, so that was just me being a little unnoticing of that. Moving on to number 25. So in 25, again, it's asking us to calculate the Kc for this chemical reaction. Notice that it only gives us 2 concentrations because we have a heterogeneous equilibrium. We have a solid iron oxide and solid iron. So we're not going to need to use those in the equilibrium constant expression. So Kc is equal to products over reactants, so CO2 over CO, and they both have coefficients of 1, so we don't need to, this is actually, so we don't have any exponents to worry about, and so we just need to plug this in to the plug in the numbers to find out our equilibrium constant. And so CO2 had a concentration of 0.052, and I use brackets, you can use parentheses or brackets, doesn't really matter, and we have 0.20. And so they both have only 2 significant figures, so our answer should only have 2 significant figures. And so we do 0.052 divided by 0.2, and we get a value of 0.26 is our equilibrium constant for that reaction at 750 degrees Celsius. Now we'll move on and look at LeChatelier's principle and how we affect the equilibrium and how we shift the reaction based on these changes to the reaction. So here we have oxygen making ozone, and so basically we want to figure out if the reaction is going to shift toward the products or toward the reactants, or if it's not going to change at all. So if we add oxygen gas, that means we're going to add a reactant. If we add the reactant, we have too many reactants, and so it's going to have to shift toward the products. So it's going to shift toward the products. All right. We'll just write, well, to make it more Alright, if we add more ozone, we're going to add a product. We're going to increase that, and so when we increase the product, then we're going to shift it toward the reactants and to balance it out. You can almost just kind of write these arrows so they kind of flow. If this goes up, then it's got to move over to make more of the reactants. Increased temperature, we said we wouldn't have to worry about the temperature problems because we didn't go over endothermic and exothermic reactions in the course. And D, increase the volume of the container. So if we increase the volume of the container, that's going to favor the side that has more moles of gas. The volume is going to be larger, and so we can allow more moles of gas to be present. And so here we have, in the reactant side, we have 3 moles of gas. In the product, we have 2 moles of gas. So the side that has more moles of gas is favored. So we're going to shift toward the reactants. And then if we add a catalyst. So a catalyst lowers the activation energy. And so what it does, it allows the reaction to get to equilibrium faster, but it does not change the amounts of reactants or products. So it does not change or shift the reaction in any way. It just makes the reaction get to equilibrium faster. And so here in E does not change. And we'll do one more example of LeChatelier's principle in number 35. Here we have hydrogen gas reacting with chlorine gas, and we are making hydrochloric acid gas. And so I'm just trying to figure out if it's going to shift toward the products or toward the reactants. And so I'm just going to write products or reactants. And so if it shifts towards the products, I'm just going to write products. If it shifts toward the reactants, I'm just going to write reactants. All right, so if we add more H2, add more hydrogen gas, and then it's going to go in that direction. It's going to shift toward the product. It's going to shift toward hydrogen chloride or hydrochloric acid. And so it's going to be products. Increased temperature, don't worry about. All right, remove some HCl. So here we're decreasing some HCl. And so we're losing some of the product. So it needs to be replenished, needs to be replaced. So it's going to shift toward the products again to replace it. If we add a catalyst, remember we just went over that. So we add a catalyst, it does not change the number of reactants or products and shift the reaction in any way. All it does is speed up the reaction, speeds up the time that is required to reach equilibrium. So here it does not change. And then remove some Cl2. If we remove some Cl2, then it needs to be replenished. We lost some of that reactants, and so it's going to have to shift toward the reactants to replace it. And that pretty much summarizes what I expect you to know from this chapter. You don't have to, I'm not going to require you to know how to calculate a concentration of one of the reactants or products given the equilibrium constant expressions, or given the equilibrium constant. So even though that was talked about and discussed in the PowerPoint lecture, you won't have to do that in terms of what I expect you to be able to do in this course. So, but that pretty much summarizes problems similar to what is in the homework assignment. So just email me if you have any questions.